Hello math people, welcome to the next lesson in data management. We are working on the first unit, which is called Permutations and Combinations. It's a unit basically how do we count things in a fairly complex situation. So we're learning different tools to do that. In the last lesson we talked about permutations. So permutations are if I took a certain number of items and I want to know all the possible ways I could arrange them. So we call that a permutation. So I'll skip down to this definition here. So for example, if I want to know how many ways could I arrange 8 items, well the notation I use for that, because it's a permutation and I've got 8 items, so let me do an example here. So I've got 8 items and I want to pick all 8 of them and know how many ways can I arrange that. So 8 pick 8 is a way of saying this. 8p8, that's always going to be equal to 8 factorial. And the reason for that is I can choose the first position 8 ways, the second position 7 ways, and so on all the way down to the last one, which is basically I have no choice but the only one remaining. So 8 factorial is the way we arrange 8 items. And if so 8 factorial, you'd probably do that on your calculator. You would get a fairly huge number, 40,320 ways of arranging 8 items. Okay, if we took it a step farther and say, well, say we started with a certain number of items, but we only want to arrange, say, 3 of them at a time. So for something like that, we could do an example of, we're starting with 8 items, which is your n value, and we're picking 3 of those at a time. How many ways could we arrange that? So by the formula here, it's going to be 8 factorial over 8 minus 3, which is 5 factorial. And hopefully you remember from the previous lesson, you can reduce this down because 8 factorial includes 5 factorial, but it's got an additional 8 times 7 times 6. So we could reduce it to that, or you could actually put in your calculator and get the same answer. For this, you're going to get 336 ways of arranging those 3 items out of the 8 you've chosen. Sorry, out of the total 8. Okay, so we're going to add a little wrinkle to this for this lesson. You can tell by the name of the lesson, permutations with some identical elements. So what if some of your things you're choosing are exactly the same? So for example, you could be picking red marble, different marbles, same, they could have the same color, they look identical. The best way of thinking of this, what we're going to talk about today, is words and the letters. How many ways could we rearrange certain words? Okay. Now, before we get to the formula, which is here, I'm just going to actually do one of the examples that's coming up in a couple of questions. I'm going to take the word doll. So I want to come up with all the arrangements of the word doll. Now, if these 4 letters were all unique, it would be a fairly straightforward question. It just, since if they were unique, it'd just be, I could choose one of the 4 letters. I could choose 4 letters for the first position, 3 for the second, 2 for the third, and 1 for the last, just like we have been working with before. But if there's identical things, like we have an L twice here. Okay, so we're going to have permutations that are duplicates of each other. So we don't want to count those duplicates. We just want to know how many unique arrangements we could have. Okay, so the best way I can show that is maybe to put a little subscript. Since we have 2 L's, I'll have an L1 and an L2. Now, the way they'll actually look when we do our arrangements, the L's are, you can't differentiate between the two, but in terms of the combinations, I want to show where these duplicates will occur and how we can eliminate them. Okay, so I'm going to write out all the different arrangements. So I'm going to just pause the video and I'll come back with all the arrangements done. Okay, and just like that, you could see I've got all these arrangements. It turns out I've got 24 arrangements, and that makes sense because if these letters were unique, it would be 4 factorial arrangements, which is 24. So this would be all the different arrangements. You can see that I've differentiated between the L's with L1 and L2. So in this column of 6, I've got all the words or arrangements that start with D. Second column starts with O. Third column starts with the L1. Fourth column starts with the L2. Now what I want to do now is eliminate any duplicates. So as I go through here, if I see 2 words with just the L1 and L2 reversed, I'm going to eliminate that. And right away you can see the second combination is DLL, just like the first. So I'll use this one and I'll eliminate that because it's a duplicate. And as I go down here, what do I see? I see here I've got another duplicate, DLLO, DLLO. So I'll eliminate that. I'll keep the first one. And also this combination here, the set is the same, DLOL, DLOL. So I'll eliminate that, keep that one. So I've only got 3 unique words from the first column out of 6. Okay. If I go to the second column, again, you can see I've got a duplicate right away, ODLL. So I'm going to keep the first one, eliminate that one. And I can see another one here, OLLD, keep the first one. And then again, these 2, OLDL. So I'll take out the second one. And again, I've got exactly half of the 6 that I started with. Now these 2 here, since I'm starting with one of the L's, the last one will start with the other L, L1s and L2s, and you can see these are all duplicate words, LDOL, LDLO, etc. So basically, all these are duplicates of the third column. So I'm going to use all 6 of these, none of these. And if you add up, how many do I have? I got 3, 3, and 6. So number of arrangements is equal to 12. Okay, now you don't want to have to do that every time, but I just wanted to make a point here that for every real word, I've actually got 2 ways of doing it because I've got 2 duplicate L's that I could interchange back and forth. So if you think about it, if I started with 24, 4 factorial, I divide that by 2, I get the 12. Okay, so you can kind of see where the formula is coming from that we're going to come up with here. So the number of permutations of a set of n objects containing a identical objects of one kind. So this is with multiple duplicates. So we got A duplicates, B duplicates, and C duplicates, all of a different letter or kind. The formula would be n factorial, which is the number of letters you start with, and you're dividing by each of the sets of duplicates, the factorial of that number. So for this, if we used the formula that we just developed or just looked at, it would be 4 factorial, and since we have 2 L's, it would be over 2 factorial. So that's 24 divided by 2, which is equal to 12. Okay, so we could go, we don't have to do this every time, but I wanted to illustrate where this comes from. Now, what happens if you would have 3 duplicates? Well, we're going to do an example like that, but you might think you take the 4 factorial and divide by 3 because there's 3 objects, which would be wrong because it's actually you're dividing by 3 factorial. Just like here, you weren't dividing by 2, you're dividing by 2 factorial. Now 2 and 2 factorial happen to be the same number. So it's a little misleading. You might think it's just dividing by the number of duplicates, but it's the number of duplicates factorial. And that's because if I had 3 duplicate letters, well, how many ways could I arrange those 3 duplicates? It'd be 3 times 2 times 1. I would actually have 6 duplicates if I had 3 of the same letters. So I would divide the grand total by 3 factorial or 6. Okay, so we're not going to write all the different permutations out, but I just wanted to do one example where you could actually see it. So now we're actually just going to use the formulas that we've looked at. So again, it's n factorial over the number of duplicates factorial. So you could have many different sets of duplicates, which you'll see later in these examples. So this first example, we've got the word dole, and in this case we don't have any duplicates. We do have 4 letters, so our n value is 4. So the number of permutations is going to be n factorial, which is 4 factorial. And in this case, we don't have any duplicates, so we could just leave it as this formula. Or, you know, if you wanted to put a 0 factorial here, you could. I would just write the 4 factorial. If you don't have any duplicates, why make it more confusing? And that is 24. So there's 24 arrangements of the word dole. Okay, now this should seem familiar. This is the word that we just worked with, doll. And we already know the answer is 12, so let's see the way we would do this with just the formula. So the number of permutations Okay, now we've also got 2 L's. So I'll just put a L2, meaning we've got 2 letter L's. So that means we got 2 duplicates. So our formula now will be forced to use the new version for the duplicates. So it's going to be n factorial, which again is 4 factorial over 2 factorial, which you could do it a couple of different ways. That would be 24 divided by 2. So 12 ways of doing it, just like we saw when we did it manually. Okay. Now here we've got, again, slight variation on the word, and so we have 4 letters. This time we have 3 L's. So how is that going to affect the number of words or permutations? Okay, so again, it's going to be n factorial, so same 4 letters, or at least 4 letters. And this time we want to eliminate the duplicates with the L's, so that's going to be over 3 factorial. So that's actually going to work out to just 4, which seems pretty low. But one way of thinking about it is you've got everything's an L except for that letter O. And how many different positions could I put that letter O? Well, I could put the letter O in the first position, second, third, or fourth. So I really just have 4 options where to put the L, and that agrees with our calculation here. So that makes sense on a couple of levels. Okay, let's go to the next word problem. Tanisha is laying out tiles for the edge of a mosaic. How many patterns can she make if she uses 4 yellow tiles and 1 each of blue, green, red, and gray tiles? Okay, so let's just kind of put this, we could almost like turn it into a word permutation problem. I've got, she's going to, for each of her patterns, okay, she's going to have 8 tiles, so n equals 8. And she's got 4 yellows, so I'll do 4 Y's. She's got a blue, a green. Now I've got green and gray, which kind of messes up my lettering, so I'll put GN for green. And I got a red and a gray, so I'll put GY for the gray. So I basically got, you could almost think about how many different words can I come up with this. although we're not considering the two G's to be, actually, so those are two different letters, but these are all the same. So in terms of identical letters, I do have some, and that's the Y's. I've got, if I put this here, I've got 4 Y's. So in terms of how many different patterns, I'm just going to use that same formula that I did for the words. So that's going to be n factorial, which is 8 factorial. And I've got my 4 Y's. The other ones are all unique. So I just have the one duplicate of 4. Okay, so 8 factorial over 4 factorial. This simplifies down to 8 times 7 times 6 times 5, which is equal to 1,680 patterns that she could make. Okay, so hopefully that makes sense if you think about it more in terms of making a word instead of making a pattern. You could use the letters for the different elements of the pattern. Okay, here's another word problem. Sorry, word as in we're working with a word. The word bookkeeper is unusual in that it has 3 consecutive double letters. So there's something you learned today. You can see we got some double O's, we got double K's and double E's, which I'd probably have a hard time coming up with another word that has 3 consecutive double letters. Not sure how many there are. But how many ways could we arrange the word bookkeeper to the number of unique words, or not so much words, but arrangements? Okay. So again, we're going to count up how many letters are in this word. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our n value is 10. And now I'm going to look at the duplicates, so I can definitely see. It's always good to just start with the left and work your way right. So B's, there's only 1. O's, we have 2. K's, we have 2. And E's, have to be careful with this one, we've actually got 3. And the P and the R, we just have 1 of. So these are the ones we have duplicates or repeated letters. So this should be no problem with our formula. So the number of permutations is equal to n factorial. Now this time there are more than one duplicate letters, so for each one we have to put each one as a factorial. So that's going to be 2 factorial times 2 factorial times 3 factorial. And I'll just let the calculator do this one, but this works out to some probably higher than you would expect, 151,200 different arrangements of that word. Okay, but you definitely tell that this formula is much quicker to use than actually writing out. I think you'd take several days to write out, several weeks probably, to write out all the permutations and then start eliminating the duplicates. Whereas if you've got the formula, you just plug in, you do this little mini calculations and plug these numbers into the formula and use your calculator. Okay. Last question. Barbara is hanging a display of clothing imprinted with the school's crest on a wall in the cafeteria. She has 5 sweatshirts, 3 t-shirts, and 4 pairs of sweatpants. How many ways can Barbara arrange the display? So I guess we have to assume it's an assumption that the sweatshirts are all the same. The 5 sweatshirts identical, the t-shirts are identical, and the sweatpants are identical. Otherwise, it would just be, if there weren't identical elements, we wouldn't have to use this formula. So the assumption is the sweatshirts are identical, t-shirts identical, sweatpants identical, not different colors or sizes. So how many ways could she take these clothing items? and arrange them? Well, the first thing we do is count up how many we have. We got 5, 3, and 4. So that's 8, 12 items. So that means our n value is 12. Okay, and then not sure how we're going to do this, but sweatshirts, we'll say SS. We have 5 of them. We have 3 t-shirts and 4 pairs of sweatpants, for lack of a better way of defining these. Again, for the number of arrangements on the wall that she could have, we're just going to use that same formula. So it's n factorial, which is 12 factorial, over 5 factorial times 3 factorial times 4 factorial. Okay, just for fun, let's maybe show how we can work with these to avoid the calculator if we can, maybe. Okay, so the first thing I would look at here is the 12. I'm going to pick the biggest 2 numbers on the numerator denominator. I've got a 12 factorial, 5 factorial. So if I cancel those, basically that leaves me with on the top 12 times 11 times 10 times 9 times 8 times 7 times 6, because those cancel out. And then on the bottom, well, I've already got rid of the 5 factorial by doing that. The 3 factorial, that is 6, so I'll just do the math in my head there. And the 4 factorial would be 24. Okay, now what I can do is I can actually cancel the 6, top and bottom. And I don't have a 24 up here, but I've got a 12. So I can cancel the 12 and reduce this to a 2. And then just to be totally complete, I can take an even number up here and to cancel this 2. So let's do the 10 reduces to a 5 divided by 2. And this actually gets changed to a 1. So now in the bottom I've just got a 1. So what do I have left over? Just clean this mess up. I've got 11 times 5 times 9 times 8 times 7. So I won't do that in my head, but at least I did some mental math here to reduce it. And I could do this in my head maybe if I felt like it. That works out to 27,720. So there's a lot of ways she could hang those school clothing items on the wall, even though a lot of them are identical. Okay, so that's it for this lesson. We got some homework that I've assigned here to help you practice this. And I believe in the next lesson we're going to be starting working on combinations. Okay, very similar to permutations, but a very important difference. Okay, so see you in the next lesson. Have yourselves a great day.